So in this lecture we are going to start this topic called gravitation. So this topic is also called Newton's law of gravitation because the law that we are going to study here is very fundamental. It relates to one of the fundamental forces in the universe. One thing to be noted, this law is not related in any way to the three laws of Newton that we studied in dynamics. That's different. This is different. So let us get straight to the idea. As per Newton's law of gravitation, let me state it. Law of gravitation. Okay, and we will understand the law for point masses. What happens if the mass is not point sized? If it is having some size and so on, that we will see later. So any two point masses m1 and m2 separated by distance d attract each other. Attract each other with a force which is proportional to product of those masses and inversely proportional to the square of distance between them. This is the statement for the law of gravitation, which is also called universal law of gravitation, because the statement which I am giving works for any 2-point masses in the universe. So let us understand what this is saying. Any 2-point masses, that means any two masses having size tending to 0, separated by distance d, attract each other with a force which is proportional to product of those masses and inversely proportional to square of distance between them. That means if I have a point mass m1 here and another point mass m2 here, separated by a distance of d, then what this law is saying is m1 is going to attract m2 like that with a force. m2 is also going to attract m1 with force. The magnitude of both these forces is F only. This F is proportional to product of masses and this F is inversely proportional to square of distance between them. So we can combine these two proportionalities. What do you mean by proportional? If m1 increases, the mass of first particle increases, the force it experiences will also increase. The force it exerts on another particle will also increase. That is something very strange. If m1's mass increases, the force m1 experiences also increases. The force m1 exerts on another particle m2 also increases. This is what is found to be the law of nature. So force is proportional to m1. Similarly, force is proportional to m2. So this gravitational force depends on the mass of the object which is experiencing the force. It depends on the mass of the object which is exerting the force. So this force depends on the mass of the object experiencing the force and also on the mass of the object exerting the force, and inversely proportional to square of distance. So if you increase m1, force is going to increase. If you increase m2, force is going to increase. So if you increase both m1 and m2 simultaneously, force is going to increase by huge amount. Depends on their product. And similarly, if you increase the distance between these objects, as the objects get farther, the force is going to reduce. So it is proportional to 1 by d square. This has been observed by nature. So we can combine this and write F is in general proportional to m1 m2 by d square totally, because you could be increasing m1 simultaneously increasing distance. Due to increase in m1, force increases, but due to increase in distance, force decreases. So it works this way. And whenever there is a proportionality, you can convert it into equality by introducing appropriate constant. And in this case, this constant is called universal gravitational constant, because wherever you go in the universe, this constant value is going to remain same. Universal gravitational constant, and its value experimentally has been found to be 6.67 into 10 power minus 11 Newton meter square per kg square is the unit. So this is a universal gravitational constant. That means whenever you take any two objects and you are trying to find the force that one object exerts on another because of gravitation, this constant will be used. Its value is 6.67 into 10 power minus 11. Of course, we have first given this law of gravitation for point masses. If it is not a point mass, we will look into that later. But some things to be noted, some important points. Gravitational force is always attractive. This is a very interesting point. Gravitational force is attractive. Okay, and this is first point. Second, this gravitational force acts along the line joining both the particles. Gravitational force acts along the line joining both particles. So you can see here I have m1 and m2. First I joined them by the line, the blue colored line. So the gravitational force acts along that line. For instance, if I have a particle here m1 and if I have a particle here m2, first you should join these particles by a line. Okay, so like that. Along that line the force will act, and because it is attractive force, on m2 the force is towards m1 and on m1 the force is towards m2. It will always act along that line. Okay, that is very important. So whenever you want to show gravitational force, first you join the 2 point masses with a line, then you show the force as attractive acting along that line. Then you see, if I call this force has magnitude f some direction, this also has magnitude f but opposite direction. In fact, these two are action reaction pairs. If you call one of these forces as action, the force that acts on m1, if you call as action, the force that acts on m2, this is called reaction. Okay, both are acting on different bodies. So gravitational force, just like any other force, comes as action reaction pair. So just like any other force, gravitational force comes in action reaction pair, just as any other force. So both action and reaction pairs have same magnitude but opposite direction. Okay, so both always, this is Newton's third law, both action and reaction pairs have same magnitude and opposite direction. They act on different objects. They don't act on same object or same body. They act on different bodies. That means if you say action is acting on m1, a reaction should be acting on the other object, which is M2. In fact, you can call even the force on M2 as action, then force on M1 will be reaction. There is no first and second here. Both action and reaction act simultaneously. Any one can be called action, other will be reaction. For example, you push a wall pushes you. Now, wall pushing you can call it action, and you pushing wall can be reaction. You might immediately jump and say, no sir, I first pushed the wall, but that is wrong. Do you think you first pushed the wall and after 1 hour the wall pushed you? No, na. The very instant you touched the wall touched you. You are thinking I touched the wall is thinking I touched you. So the very instant you touch the wall and try to press it, the wall is pressing you. So the very instant both these pairs of forces have come into picture, action has come into picture and reaction also has come into picture. Okay, so you can call any one as action, other will be reaction. So both action and reaction pairs have same magnitude, but they have opposite direction. They act on different bodies. Okay, they are simultaneous. They act simultaneously. This is very important. They act simultaneously. It is not that first you have action, then after some time reaction acts. No, both act simultaneously. So here in Newton's law of gravitation, the very instant M1 is exerting force on M2, that very instant M2 is exerting force on M1. Is this force instantaneous? For example, if these two point masses are kept some light years apart, do you think M1 will immediately exert force on M2 and M2 immediately exerts force on M1? Well, this question is very tough to answer, but I think gravitational force is just like light. So, for example, light will take some time to travel from one place to another if it is some light years away. So, if M1 is kept in one galaxy and M2 is kept in another galaxy, then the force will not be immediate. Okay, the interaction will take some time to reach M2. The force exerted by M1, it will not happen immediately on M2. It will take just the same time that light takes to reach M2. Na? After that time, there will be a force on M2. How and why we will see later in the concept called field. We have something called gravitational field where we will look into this particular point. Now, what if the object is not a point object? Suppose if I have a big sized object of mass m1 and another big sized object of mass m2, definitely this m1 is going to attract as a whole. If you take it as one system, this m1 is going to attract m2 and m2 is also going to attract m1, because as per Newton, any two objects in the universe, no matter what their size is, they always attract each other with a force. This attractive force is called gravitational force. It is always attractive. So m1 is going to attract m2 and m2 is going to attract m1. So on m1 there will be a force, if I say F. In fact, it will be acting at, you can say, center of mass of m1. On m2 there will be a force F. Okay. This may not even act at center of mass. I may be wrong. Anyway, I'll come back to that later. But how do you calculate this force value? What distance you will take? See, it is not always correct to take distance from this center of mass to this center of mass as d. This is not always correct, not correct. It is correct in some cases, some symmetrical cases. We will come into that. But the technique to calculate force between m1 and m2 is, we will chop m1 into many point-sized particles, and number of them will be very huge. It will be infinity. So I am visualizing m1 as made up of many particles, okay, each of almost zero size. Such particles are making m1. The number of such particles is infinity. And similarly m2, I am again visualizing it as many particles. Okay, wherever there is a gap, there also there is a particle. It's very difficult to show. Just I am showing some dots here and there, but the whole body is composed of many point masses. So what you should do, you take one point mass of m1, find force on it due to every point mass of m2. So this point mass of m2 exerts a force. This point mass of m2 exerts a force. This point mass of m2 exerts a force. Like that, you find force due to every point mass of this object on this point mass. That is 1. Similarly, find force on this point mass due to every point mass of second object. That is 2. Find force on this point mass due to every point mass of second object. 3. Find force on this point mass due to every point mass of second object. 4. Like that, you find force on every point mass of m1 due to every point mass of m2 and add it up. That means you add all these 1, 2, 3, 4 forces so on to get net force on m1 due to m2. So I hope the idea is clear now. What we are doing, we are chopping the first object into many point masses, infinite number of point masses. We are chopping the second object also into infinite number of point masses. On every point mass of m1, you will find force due to all point masses of m2. On every point mass of m1, you will find force due to all point masses of m2 and add it up to get net force on m1. Suppose, to just give you some very crude example, suppose that an object has here 3 point masses 1, 2, 3, and second object has 3 point masses 1 dash, 2 dash and 3 dash. So you will find force on 1 due to 1 dash, force on 1 due to 2 dash, force on 1 due to 3 dash, force on 2 due to 1 dash, 2 due to 2 dash, and 2 due to 3 dash, and force on 3 due to 1 dash, force on 3 due to 2 dash, and force on 3 due to 3 dash. Add all these forces, that is the total force acting on first object. Okay, so this is what you should do if it is not a point mass. And if it is a continuous object, a big object with no gap, okay, then we will use this technique of integration here. This chopping the body into small pieces is called taking an element, then finding force on that element due to another element of the second object and integrating both these objects to include all the particles. So the technique of finding the force really involves integration. In fact, this problem of gravitation led Newton to bring out this new subject of mathematics called calculus. That is the idea. So we are going to see that now, how this is done in more complex cases with integration. We are going to see that when we do 1 or 2 examples. But first, let us come to simple examples. Simple examples. I'll show you the more complex examples where integration is involved later. First, let us take a 1 kg point mass. Generally 1 kg object will occupy some size, but here I am taking 1 kg point mass, another 1 kg point mass separated by, let us say, 1 meter, which is not a very big distance. Let us try to find the gravitational force between them. So the left 1 kg is going to pull the right 1 kg in that direction with a force F. The right 1 kg is going to pull the left 1 kg in that direction with a force F. So let's get the magnitude of this force. The magnitude of this force is given by G, m1 is 1 kg, m2 is 1 kg by r square is 1. And G value is 6.67 into 10 power minus 11. Totally we are measuring force, so we measure it in newtons. You see this 6.67 into 10 power minus 11, it's such a small number. If I write it, it is newtons. Such a small force is almost negligible. So you see, gravitational force is a very, very small force. It appears big for us because the size of the planets, the sun, etc. are very huge. So it appears to be big for us. But if the mass is 1 kg and 1 kg and distance is 1 meter, the gravitational force is really very, very small. So between two 1 kgs, the gravitational force is very small. Now there is a common question. Suppose on a table, if I put two 1 kg objects separated by 1 meter, of course, let us assume this is a frictionless table for a minute. Normally every table has friction, but let us assume it's a frictionless table. Then this left 1 kg is going to attract right 1 kg, right 1 kg is going to attract left 1 kg. So slowly they should start moving. Of course, you might say this force is extremely small. This force is extremely small. So the acceleration of these two objects, force by mass, will also be very small. So the velocity they gain is very, very small. So they will be moving very, very slowly. Okay. So we don't see them moving. But actually, if you wait for 1 year, maybe they move. But in practice, actually, they don't move. You know, suppose let me do some calculation. The force is 6.67 into 10 power minus 11. So the force is 6.67 into 10 power minus 11. This force acts on the left 1 kg also. This force acts on the right 1 kg also. So if I take the left 1 kg, I know the force on it. So acceleration is force by mass, 6.67 into 10 power minus 11 by mass is 1 kg. So this is acceleration. Initial velocity is 0. Let's assume this acceleration is constant. It is not. As the objects come closer, the force will increase. Acceleration will increase. But let's assume it's a constant acceleration. Let me assume. Okay. And find time for this to travel half meter. Okay. So displacement is half meter. Why half meter? By the time this travels half meter, that would also have traveled half meter. Na? I'm finding the time assuming constant acceleration, but actually the time will be much lesser than this because acceleration will increase as they start coming closer. Let us find the time for them to travel half meter. Okay, so S equal to ut plus half a t square I'm applying, which I should not apply because a is actually not constant. But let's find the time in this case. I'm finding a much greater time. In fact, they will meet in a much lesser time than what I am calculating because acceleration is becoming more and more. So S is half a into t square. So t square will be 1 by 6.67 into 10 power minus 11. So it will be 10 into 10 power 10 by 6.67. So t will be root 10 by 6.67 into 10 power 5 seconds. So in this time they should meet, or in a much lesser time actually, because as they come closer, the acceleration is increasing. So if I calculate this time, so it comes out to be 1.22 into 10 power 5 seconds roughly. Okay, 1.22 into 10 power 5 seconds. This is the time. So if I convert it into hours, 1.22 into 10 power 5, this is in seconds. Na? If I do it in hours, it's 3600. So 1.22 into 10 cube by 36. So 1220 by 36. Okay. So it comes out to be 33.8 hours, which is less than 2 days. So in 2 days, I should see these two objects coming closer and touching each other. Let us do this experiment on Earth. Let us take a table, put 1 kg here, and come and check after 2 days. Do you think they will come closer? No. Of course, you will immediately say, sir, there is friction which was not allowing these objects to move. But I can have an experimental setup, where I can have some V-shaped, this is a very standard experimental setup, a V-shaped metallic uh, object with air pores, where you will be having air blowing from those, and there you keep the objects in air, they'll be hanging in air. Okay, such an experimental setup is possible. Then you can keep 1 kg separated by 1 meter, where they will be floating in air, and then air resistance can be neglected, okay, compared to the resistance by table. But still you don't see these objects coming closer after 2 days. As per Newton's law of gravitation, there is a force, so both objects are attracting each other, they must come closer. But when we do this experiment, we don't see objects coming close. The problem is, we are thinking like this. When you take a table, for example, we are thinking, I place 1 kg object, I place another 1 kg object. This 1 kg is attracting that 1 kg, that 1 kg is attracting this 1 kg, they should come closer. See, the problem with this argument is, I know that 1 kg object, the left 1 kg A is attracting right 1 kg B, and right 1 kg B is attracting left 1 kg A. Correct, no doubt. But why should A move towards B? Immediately you will say, sir, there is force. No, sir. But you are staying in the room, you are attracting 1 kg, the wall of the room is attracting 1 kg, the bus going outside the room is attracting 1 kg, the ceiling is attracting 1 kg, the floor is attracting 1 kg, the table is attracting in some direction, some ant somewhere in the room is attracting this A. So many forces are acting on A. Why it should only go towards B? This is my question. Do you think you have put A and B somewhere deep in outer space where no other object is there, and hence A should move towards B? That is okay. But here on earth, so many objects are there. The walls of the room itself will attract A. So why should it go to B? In fact, the correct argument is, on A, there are so many forces. There is force by B, there is force by wall, there is force by bus, there is force by this, by that. Net force on A will be 0. So A will stay there only, that's it. So don't conclude in the wrong way that gravitation is wrong. Gravitation is there, but every object attracts A. So don't say, sir, I put A and B on table, A should move towards B now. No, A need not move towards B, because B is not the only one exerting force on A. The wall has mass, it exerts force on A. The roof has mass, it exerts force on A. So many buildings are there in our colony, each will exert force on A. Aeroplane going in the sky will exert force on A. The train going on a track will exert force on A. Sum of all these forces, so many particles are there, that sum of all these forces somehow is 0 totally on A. If you really want to understand gravitation, take A and B to outer space, where very far away from all planets, stars, galaxies. Put both of them there in outer space, separated by 1 meter. Come back, again go after 2 days, you would see they both would have touched each other. That is true. So you should be very clear with the arguments. Okay, there are very tricky arguments, you should be very clear with the arguments. Now let us go to our next example. Suppose if there are 3 particles. So the next example is like this. I take my x and y axis. Suppose there is 1 kg mass here kept at origin, there is 2 kg mass kept at 0, 2, and there is a 4 kg mass kept at, let us say, 2, 0. And right now somebody is holding these masses, let us say, so that they don't come closer. We have to find net force on the 1 kg mass due to 2 kg and 4 kg. Find net force on 1 kg mass due to 2 kg and 4 kg. So here what I want to lay stress on is the vector nature of force. So if I show with the diagrams, the 2 kg is going to attract 1 kg along the y axis, and 4 kg is going to attract the 1 kg along x axis. Both these forces you have to add vectorially, because force is a vector quantity. Let's first find the force on 1 kg due to 2 kg. It will be G 1 into 2 by distance square 2 square. And similarly this force will be G 1 into 4, because this is 1 kg, that is 4 kg, m1 m2 by r square, again 2 square. So this is going to be, first force is going to be G by 2 Newton, second force is going to be G Newton. So on 1 kg there is a G Newton and there is a G by 2 Newton, both are acting perpendicular. So resultant force on 1 kg will be root of G square plus G by 2 whole square under root. So that will be G root 5 by 4, is it right? Newton. So that is the net force on 1 kg due to 2 and 4 kg in some direction. What is the direction? With x-axis we will find the direction that this net force makes. Tan theta is G by 2 by G, so 1 by 2. So net force acts at an angle of tan inverse 1 by 2 with x-axis. The value of the net force is G root 5 by 4. So the only thing I am saying here is this force is a vector quantity that you should keep in mind. So when you are adding forces, you have to be careful. Let's look at an interesting question. 4 particles, this is a very beautiful question. 4 particles, each of mass m, are symmetrically moving with same speeds in a circle of radius r due to mutual gravitational forces. Find speed of any one of the particle. So here we are looking at a very interesting thing. The gravitational force is responsible for circular motion. See, whenever any particle goes in a circle, there must be some force towards the center of the circle. For example, if a car is taking a turn on a circular road, the force towards center of circle is friction on the wheel, the sideways friction on the wheel, that is responsible for the car taking turn. If there was no friction, just the wheel would turn but car will not turn. Car will be sliding. Okay. Similarly, when a stone tied with a thread goes in a circle, okay, on a horizontal table, it is the tension force of the thread towards center making the stone go in a circle. Similarly here, the 4 particles are moving in a circle of radius r in deep outer space because of gravitational force. So in a symmetric way. So let us draw the diagram of this. So if I first draw a circle, I will place 4 particles here. One particle here, here, other here, here, all are mass m. So you can choose any one particle and calculate the forces on it. So if I show it, there is a force like this due to the top particle on the left particle, and there is a force like this due to the this particle, and there is a force like this. The resultant of these forces is towards center by symmetry. Hence on every particle there is a net force towards center. Now if I take this radius is r na, so this distance, this will be r root 2. Similarly this distance, that will be r root 2, and this distance to the other particle here will be 2r. So let us first get the net force on the left particle. You could have chosen the right particle also or top particle also, any one, and you can just do the analysis. So on the left particle there is a force like this, G mm by r root 2 whole square. Okay, G mm by r root 2 whole square. Similarly here there is a force by the down particle, same, G mm by r root 2 whole square, and this force is given by G mm by 2r whole square because that distance is 2r. So we have to get the resultant of these forces. So now these two forces, which one I am showing in the red color, this and this are perpendicular. The resultant will be in this direction only. So that resultant force will be gm square by 2r square into root 2 plus this force gm square by 4r square. So you can write gm square to 2 root 2 plus 1 by 4r square is the net force towards center. This force is responsible for the circular motion of that leftmost particle. Okay, this force is responsible for the circular motion of the leftmost particle. So this force should be mass into acceleration, which is v square by the radius. Each particle is going in a circle of radius r. We are considering the left particle now. It is going in a circle of radius r. So F equal to ma I am applying. So gm square into 2 root 2 plus 1 by 4r square is mass into acceleration v square by r. So one of the m gets cancelled, one r gets cancelled. So the speed of this particle or any particle, because all are moving symmetrically, is gm into 2 root 2 plus 1 by 4r. That is the speed of every particle that is going in the circular path. So this idea we will later take up in what is called orbital velocity of a satellite around Earth, or in general orbital velocity of a planet around Sun, and so on, with certain approximation, because we neglect gravitational force due to other celestial bodies except the one we are considering. In case of satellite, we assume only Earth exerts gravitational force and calculate orbital speed. So we will use this concept later in what is called orbital speed. Now let us look at another example, a very interesting example. Suppose if I have 2 point masses and somebody is holding them, they are separated by a distance d. Somebody is holding them so that they don't run away or come closer due to gravitational force. Now a third particle is kept at different points on this perpendicular bisector. So let me draw the perpendicular bisector. This is the, let me draw it a bit side. This is the perpendicular bisector. So a third particle of mass capital M, first if it is kept here, the force on that will be 0. Why? The left mass is going to attract it, the right mass is going to attract it, and both these forces have same magnitude, it cancels. But if you keep this M here, the left mass is going to attract, the right mass is going to attract, this sum is not 0, it will be downward. If you keep it here, again the left mass is going to attract, the right mass is going to attract, again this sum is not 0. But if you go like this and go to infinity, at infinite distance, gmm by infinite square, I should not write like this, I should write d square and d tends to infinity, the force is 0. So you see force at point O is 0. When you keep m at O, force is 0. Then as you are going above, force is not 0, not 0, not 0, not 0, not 0. But when you reach infinity, again force is 0. So as you go from O to infinity, force goes from zeros to 0. As you keep moving m, from O to infinity, force goes from 0 to 0. So somewhere at some point, let us say P, some point P, the force has to be maximum. Find a distance OP so that the force at P is maximum. Force at point P on the capital M is maximum. So at what distance from O on perpendicular bisector is force on M maximum? It has to be maximum, na? because at O force is 0. Then as you start going above, force is not 0, it increased. Then again when you go to infinity, force becomes 0. So something is going from 0 to 0. It has to increase and then decrease. Okay. Suppose your height was 0 today and after 4 years again it is 0. In between you might have grown and again decreased in growth. If it is possible. It's a hypothetical example I am giving. So there is a point where you reach a maximum height. After that you decreased. So here also the same thing. So you have to find that distance where force on capital M is maximum. So this is a problem related to maxima minima. So how do we do that? So we do it like this. This is M. This is also M. At certain distance x, let us say the force is maximum. This is d by 2 and this is d by 2. So we'll find force on this capital M at that distance. So how to find that force? First we'll find force due to the left small m. That will be gmm by this distance square, which is x square plus d square by 4. Similarly on m due to the right small m, the force will be again gmm by x square plus d square by 4. If you take this angle as theta, the net force on m is gmm by x square plus d square by 4 cos theta plus gmm by x square plus d square by 4 another cos theta. So here I am just writing another cos theta. So basically this red colored force, one component, downward component, and this red color force, downward component, add up. Horizontal components cancel. So the net force I can write it as 2 gmm by x square plus d square by 4, and cos theta from the figure is adjacent by hypotenuse, x by root x square plus d square by 4. That is cos theta. That is the net force on M. Okay. It depends on the distance x. What is x here? X is this distance. Okay. So the force as a function of x, I have got it. Let me write it on next page. The force as a function of x is 2 gmm x by x square plus d square by 4 whole power 3 by 2. Okay, that is the force as a function of x. You can see if x is 0, force is 0. What is meant by x is 0? This m is exactly at midpoint of the two smaller masses. Okay, and if x tends to infinity, you can use limits. Limit x tends to infinity of 2 gmx by x square plus d square by 4 whole power 3 by 2. That is also 0. You can check it. Because the numerator is only x, but the denominator actually is x cube. X square power 3 by 2, x cube. Okay. Actually when x is very huge, you can neglect this d square by 4. You can write this as 2gm x by x cube. So anyway that will go to 0. So in between somewhere force is maximum. Wherever force is maximum, in fact if you plot a graph of force versus x, it looks like this. Okay, initially force is 0, then it looks like this. So somewhere force is maximum, there the slope of tangent is 0, means df by dx is 0. So whenever something is maximum, derivative of that quantity with respect to some variable must be 0. So if force is maximum, derivative of force with respect to the variable x here should be 0. So let's equate that. So we have to find df by dx from here and equate it to 0. So I am doing it on next page. F is 2gm x by 2gm x by x square plus d square by 4 whole power 3 by 2. So df by dx, when you are differentiating, keep constants outside. 2gm is a constant, keep it outside. Just to differentiate the variable part, and equate it to 0. Anyway, this constant cannot be 0. So the remaining derivative must be 0. So derivative, how do you do it? You have to use quotient rule here. First square the denominator, then denominator into differentiation of numerator minus numerator into differentiation of denominator. This must be 0. So the quantity which I am circling, we must equate that to 0. Okay, so if this expression is 0, numerator must be 0. Our denominator should be infinite, but that is not the case here. So numerator must be 0. So which implies x square plus d square by 4 whole power 3 by 2 into d by dx of x is 1 only, minus x into, here you have to use chain rule, x square plus d square by 4 whole power 3 by 2. It is like some box power 3 by 2. So 3 by 2 into box power 3 by 2 minus 1, that is 1 by 2, into derivative of that box again. Derivative of x square plus d square by 4 is 2x. That is chain rule. So if I go to next page, I can write this. I will take root x square plus d square by 4 common in both terms. So you will be left with x square plus d square by 4 in the first term, because first term is power 3 by 2. If you take root 1 by 2 common, another 1 will be left. And in the second, this 2 gets cancelled. You will be left with 3x square because this term has been taken out. So this should be 0. This cannot be 0. This cannot be 0 because d is there at least. No? So other possibility is x square plus d square by 4 minus 3x square is 0. So d square by 4 is 2x square. So x is plus or minus d by 2 root 2. The minus sign is also significant here. So at this distance, force on the capital M is maximum. Minus sign is significant because plus d by 2 root 2 refers to a point here. There is a point here below which is actually minus d by 2 root 2. Basically, if you assume that way. So there are 2 points where force is maximum. So you see, whenever you get this term maximum or minimum in question, one of the approaches could be using calculus. I am not saying calculus is the only approach, but one of the lines along which you should think is maybe you have to use calculus. So if you want to find a certain quantity's maximum or minimum value, first you get that quantity as function of some variable, then use derivative and equate it to 0. So here force on M should be maximum. So first get force as a function of distance, then maximize it by taking derivative and equate to 0. So this is one of the approaches. So this is a very interesting problem in gravitation. Okay. Now, what if I have the last problem for this lecture? What if I have a rod of length L and mass M and another point mass M, and let us say the separation from this end to that point mass is A. What is the force exerted by point mass on rod or rod on point mass, whichever way, because they are action reaction pair. So find force on rod due to point mass. Suppose this is the question we want to do. Now we cannot apply Newton's law of gravitation directly because the Newton's law of gravitation statement has been given for 2 point masses, but here the rod is not acting like a point mass. So we have to do calculus. Chop the rod into many particles. So how do you do that? Now it is done like this. From this point mass M at a distance x, at a distance of x, at a variable distance x, consider a small piece of this rod whose length is dx. Generally, whenever you are doing a problem with calculus, you would take an element. Element means a small piece. Here the element is the dx, the small piece, that is taken at a distance x from the point mass. You will use the same variable x dx, y dy, theta d theta. So after a distance x, you take element dx. or after an angle theta in some other scenario, you will take a small element d theta. Okay, so here at a distance of x from m, you take a small portion dx of the rod. That dx, you can say it is a point mass. Why? Whenever you say quantities like dx, dy, dz, they are zero, they tend to zero. So this length dx is tending to zero, which means that piece of the rod is a point mass. Okay, so this is point mass. Then immediately, what is its mass? This question comes. What is its mass? So for length L, mass is m. So for length dx, what will be the mass? So it will be m by L into dx by ratio and proportion is mass of element. That is the mass of our element. That is the mass of our point mass. So now I'll find the gravitational force between m and this dx, whose mass is m by L into dx. Okay, it's also a point mass because its length tends to zero. Rod means it's like a wire. You neglect the thickness of the rod always. This is anyway tending to zero. Now in that also you took a small portion whose length is zero. So it's a point mass. And the distance between them is x. So this m is going to attract this point mass with a force, with a little force which is given by g mass of the point mass into mass of the element g m1 m2 by distance square, and that force will be to the right as shown. This is the force on the point mass of the rod. Like this, you should take different point masses on the rod. You took one at a distance x, you must take another one here, another one here, another here. That means you should cover the whole rod. How do you do that? Just by changing x. If you put x equal to a, it is as if you have taken this point mass here. If you put x equal to a plus L, you have taken this point mass there. So by controlling x, you control the location of point mass. Then you should add all these forces. Luckily they are all to the right only, because if you take the rod, if you take point mass here, force is like this. If you take point mass here, force is again in same direction due to this small m. So you can add all these forces. If forces are in different direction, you must take components and add. So here I am directly adding g mm dx by Lx square. I am adding, and I am controlling x to cover the whole rod. X will go from a to a plus L. When x is a, this dx is here. Okay, the dx is after x. So if x is a, the dx is here. If x is a plus L, the dx is there. Is it okay? So x will go all the way, taking all the values from a to a plus L. They are called limits. That will give the force on the rod by point mass. So when I do it, g mm by L is a constant. You are left with dx by x square. This integral you have to perform, this integration or addition from a to a plus L. So this comes out to be g mm by L into 1 by x square. Integral is minus 1 by x. Keep minus outside. 1 by x, limits from a to a plus L. Or you can do one thing. Absorb the minus sign and interchange limits. You can do that. First you will put upper limit minus lower limit. But if you absorb minus sign, first put lower limit, then subtract upper limit. So you will get 1 by a minus 1 by a plus L. Actually I should have written 1 by a plus L minus 1 by a, but I absorbed minus sign. So this gives me g mm by L into, if you take LCM, L by a into a plus L, this L gets cancelled. So this is the force on the rod due to that point mass. This is the force on the rod. Clearly, if you look here, okay, the value of force which we are getting is gmm by a into a plus L. Many people think that you can replace rod with center of mass. Replace the rod with a point mass at center of mass. You can't do that. If you do that, what should have been the force? This will be then a plus L by 2. The force should have been g mm by a plus L by 2 whole square. That should have been the force if you replaced the rod with a point mass at its center of mass. But the answer which we are getting here is completely different in a proper way. So you cannot always replace object with a point mass at center of mass when you are finding gravitational force using gm1 m2 by r square. Are you getting it? Okay. Because there we will see that the distance is proportional to it, the force is proportional to 1 by r square here. But there are some cases where we will prove it, or rather we'll accept that we can replace the object with a point mass at center of mass, particularly for the case of a shell and a sphere. We will see that in our upcoming lectures. So this is it for today. We'll stop here.